So last class we started talking about, what did we start talking about? So magnetic field, yes, and force on charge when they move on magnetic field, right? So we denote magnetic field by using this letter called B, just like we did for the electric field. We talked about electric field, right? So electric field comes from charge. Magnetic field can come from moving charges, okay? And these moving charges experience force when they are on magnetic field. So that force is given by, let's see, QB B sine theta. Let me write this simple way. So this is force on a charge that is moving with velocity b in a magnetic field B, where angle between velocity and magnetic field is theta. So that's what that is, right? So B is moving in magnetic field, let's say, that is going in to the, so that means in this case this theta, so B is here, so that cross means going in to the page or into the screen, okay, directly in. So we also learned that charges move in circle when it is in magnetic field. Okay, charges move in circle when it is in magnetic field. So especially the case when this angle is exactly 90 degree to the magnetic field. So if it is not in exactly 90 degree, it's still gonna move in circle, but that circle gonna shift. It's gonna become helical like a spring. But if it is exactly 90 degree, oh, that should be B, and this should be B. 90 degree, then things move in circle because force, this force acts directly towards the center, okay? So when we push something towards, directly at 90 degree, it eventually end up moving in circle. Hey, that reminds me, let's see if I have that video clip here. Oh. This thing is stuck, and you're not supposed to see this.
Maybe you have to stop sharing really quickly so you can actually move it around.
Yeah, maybe that will be easier. Let's see what happens. One more try. It is stuck in wrong place. Okay, finally found place to grab. Okay, looks like I found video, but let me make it visible. You may be thinking, what? What are we supposed to look, right? So did you notice how this ball is being hit directly, perpendicular, right? So that means force is acting perpendicular to the motion. Force is acting perpendicular to the motion. Let's watch more. Oh, yeah, this is better. So of course, this is circular motion you learn in physics 1. So basically that's what we are recalling here, okay? So when we have that, what we can do is we can use Newton's second law. Force towards the radius is equal to mass times acceleration. And if we choose this as a positive direction, then only force we have is that QVB and sine theta being 90 degree, sine theta being 90 degree, we can simply write QVB and it becomes MB square over R. So if we know magnetic field, 1V cancels here, right? So we can write something like this. So we did this yesterday. I'm just reviewing it, okay? So now, how can we use this knowledge to solve this problem? So you need to help me here, okay? How do I solve this problem using this knowledge? How do I start? One thing, note down what I know, right? So it says moving charge is proton. Moving charge is proton. Charge is E, proton. So that's elementary charge of proton and electron. That's what that is, right? So that's the charge we know. Another thing we know is we want that much kinetic energy. So kinetic energy, K, or maybe we can write Ke to make it easier to understand. So we want that kinetic energy. What has to be the radius of the proton's orbit? Okay, orbit radius is what? Where magnetic field is 1.2 Tesla. So these devices they have this you see this kind of bulk part there. So that's where the proton can move until you get a kinetic energy, right? So I'm getting some help here in chat. So let's see, multiply both sides by r and divide by qb to get r by itself. So we want radius. Okay, so that means, okay, so we want radius, so let's solve for r. Good idea. So that means I'm gonna just do the cross multiplication here. That means it's gonna be r is mb over qb. Okay, charge is known. Hey, this is proton. And that means we also know the mass. Okay, although it's not here, we can figure that out. Okay. Oh, what is mass of a proton? Does anybody know that?
1.67 times 10 to the negative 4.
Yeah, I'm hearing some voice there, but me being a bit older here, kind of hard to, like get that. But yeah, looks like somebody wrote that on the chat as well. So I think I could use that. Right? So mass is known, Q is known, B is known. And yes, charge of proton is also known, which is E, that is 1.6 10 to the power negative 27. Okay, so we know everything but the speed. And I'm getting that suggestion we need to solve for velocity using kinetic equation. Hey, kinetic energy equation. Do I remember that? Kinetic energy is, it has to do with the motion. So speed is there. Yes. So that means E is gonna be 2 times kinetic energy over mass of that proton. And it is squared, means it has to be that. Okay. Yeah, charge of electron is 19. I just copied the mass here. Okay, my bad. Okay, here, my bad. So we can use this V and find radius. Hey, now you can design accelerator that can accelerate charge, and that can be used in this kind of devices that we can use for, doing x-rays of our body, but using different mechanism. Okay. Okay, so what kind of radius are we getting? Looking at this device here, maybe it should be in order of meter, right? So are we getting that in meters? Half meter, 1 meter, something like that. So share your number in the chat, okay? That way we can make sure that everybody doing it right. So this northern light is rarely visible from Colorado, but I lived in North Dakota. Oh, that's a cold place. But once I had chance to see this northern light from North Dakota. And I hear from Alaska, it's more frequently visible, and of course, northern part of Canada, and so on. So it occurs near the North Pole and South Pole. Okay, so we being in the northern hemisphere, we only see the northern part, northern that happens in the north near the northern, pole, North Pole. So that's why it's called northern light, and northern name is aurora borealis. So what happens? Earth has a magnetic field, and these charged particles are coming and landing on the Earth. We did one problem related to that last class, right? So what happens is they may not always land exactly perpendicular to the magnetic field, as magnetic field is kind of magnetic field lines are shaped like this. Okay, so because of that, what happens is the speed may not be exactly perpendicular, so slightly inclined. So in that case, what happens is it end up making the spring-like a path. So we can think of something like this. If velocity is not perpendicular, we can always resolve velocity in perpendicular and parallel direction, right? The one that's a perpendicular component makes it go in circle, and parallel component means it's shifting, moving, right? So that way we can combine two motions, straight motion and circular motion, that makes this kind of situation. So what happens is when these charged particles hit the atmosphere, they make the electrons from the atmospheric particle jump off from there. It ionize them, and when they jump, and they can come back and recombine, so in that process they emit energy. Okay, and that energy, if it happens to be in our visible light range, then we see this colorful display. Okay, so that's how this one occurs. So what happens is these charges gets moved near the pole. Although the charges are landing everywhere, since there is this magnetic field of the Earth, what happens is the charges gets moved near the pole. So that's why this phenomenon we see occurs near the pole only. Okay, so that's the aurora borealis. That's what happens. Okay, and this is the same principle we use to make image of our body part. So the proton we accelerated, remember what happens? It's gonna go and hit our body part, and it's gonna release the energy from there, and those released energy comes out as light, some sort of light, and that can be put in a plate, photographic plate, or display, CCDs. Okay, so that's how these imaging devices works. Okay, all these electromagnetism in action. So another thing, so rather than just putting magnetic field, if we put both electric and magnetic field, what's going to happen? The charge is going to experience both electric and magnetic field. Okay, so assuming that charge is positive charge, what happens? Because of the electric field here pointing this way, this experience force in that direction, so the force, electric force, is going to be up. Now what we can do is we can assign a magnetic field. We can suitably use the magnetic field such a way that it points downward. So in this case, charge is moving up, positive charge is moving up, and magnetic fields are coming towards us, right? In that case, the force not gonna be down. But if the charge was moving sideways, let's say, charge was moving sideways, then what would be the direction of magnetic force. Can you use your right hand rule and figure out? So let's suppose the charge is moving to the right. Okay, charge is moving to the right. Charge is moving to the right. Looks like that's my right, right? Charge is moving to the right. But if I do this, the field is that way maybe. Okay, so field, if we line that, it should be, like maybe. So what happens, it can be up or down depending on which way charge is moving. So by making the suitable arrangement, we can make the force downward, force due to magnetic field downward, and electric field upward. So those two forces, when balanced, what happens? Those two, one going to be positive, another going to be negative, so net force becomes 0. So I see hand. Yes, Levi?
Wait, wouldn't the velocity be upward due to that electric field?
Yeah, if this was just the electric field, then yes. Okay. So let's suppose we insert this, we fire this charge in that region, in that direction. Okay. So in that kind of situation, what happens? We can set this up such a way that two forces are balancing each other. Let's say we set that instrument like that. We'll be seen swing, we'll be soon seeing it. Okay. So here, then what happens? If one is positive, another one gonna be negative. Which one positive, which one negative, doesn't matter much, right? So what is important here is when we have that balanced situation, in that case, we can remember object can move with constant velocity even when net force is 0. So there can be force upward, downward, balanced, and object can be moving sideways. That can happen, right? So V is that. So by setting up E and B suitably, we can actually find out what velocity we can get from there. So before we, so what happens? We can calculate velocity. So this kind of setup is also called velocity selector. Okay. So this kind of setup is also called a velocity selector. So let's suppose we want a particular speed, charge of particular speed coming out from the setup, then we can use this. And after doing that, we can put this in, the mass spectrometer. So we know speed, then we put that in mass spectrometer we talked about yesterday. And from there, we can calculate mass or charge of the charge, okay? So now there is this blood flow meter. So blood is flowing through our body, we know that. But sometimes what happens is there may be, plaque on our bloodstream, right? So when there is a plaque, what happens is the speed of the blood chain may change around that, okay? So without doing any kind of a surgery or anything, we can set up a blood flow meter near our body, hand, body part, right? And then look at how speed is changing. If speed change seems to be abnormal, then that means we can say, oh, there might be a plaque, okay? So that's how this thing is used. So let's look at here. So there are these positive and negative charges, let's say, okay? And if we apply a magnetic field on those moving ions, so moving ions means our body, bloodstream contains ionized charged particles, okay? So blood has this lot of things, including the salt, positive, negative ions, and so on, right? So think about those are the charges here, okay? Since they are flowing with the bloodstream, if we know the speed of those charges, that means we know the speed of blood flow, Okay. So let's suppose it is moving and you put your hand in that magnetic field now. Then what's going to happen? The charge is going to experience force perpendicular to the motion. So positive charge is going to experience force in one direction, negative charge is going to experience force in opposite direction. So that means these two charges are going to separate. Two kind of charges, they're going to separate. So now it looks like a charge plate, right? So it builds capacitor kind of structure right there. Positive charges, negative charges. And what's the separation distance between them? That's the width of the arteries or vein, diameter of the arteries or vein. So now you can measure voltage produced by these positive and negative charges. And by knowing distance and this voltage, you can find electric field. Okay. So once you have this electric field, and since you are using magnetic field, you know the value of magnetic field. So you can measure electric field, and you know the magnetic field means you can tell what speed they are moving. You can use this, okay? So that's how you can design a device and make blood flow meter. See, physics is everywhere. So there is question that says, is this application if E and B are in opposite direction, force due to them is in opposite direction? Okay, so in case of blood flow meter, what happens is you can orient magnetic field the way you want, right? And then set up. See, we are not applying electric field. Electric field, we are generating electric field by separating charges here. Okay, so we don't even have to worry about direction, but of course what happens, there are going to be force in one kind of charges acting in opposite direction, right? So in that case, the force due to magnetic field and electric field, they have to be balanced though, yes. Okay, so we need to orient magnetic field. We don't have control over electric field because we're not applying this electric field. They are just there. We are just separating charge and creating electric field. Okay, so our application of magnetic field gonna create that kind of situation. Okay, yes. Thank you for bringing those questions for the discussion. So you just stick the probes and then measure those, okay? Yes, B and E gonna be perpendicular, so that way we can use this formula. Otherwise, we cannot use this formula, okay? So that's about force on the charge. And now let's talk about force on current. And current is just moving charges. It's basically same thing. They are just streamlined charge we talking about, okay? So not much new here, but we can now write that equation we had in terms of value of the current, okay? And can determine the force. And there is very nice setup put together by this person here. And I got this from YouTube. You can see the address here. Does very good job demonstrating it. So let's watch.
I have here.
And maybe if I can use the computer sound, so that is going to be better, okay? But it may be loud, so be careful.
A large magnet, South Pole, North Pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force. Oh, get this guy out of the way. And there you see it.
So, see, that's where it starts, right? We just know, oh, it experiences force, and we can bring that all the way and make all these devices, okay, that we can use. So now, just like I said, there are different ways we can use right-hand rule. So this portion demonstrated a right-hand rule, but I want you to actually look at and see if you can, figure out, indeed, that's the direction of force. So let's see, where is rate connected here? Oh, which hand the red thingy is there? Hard to tell. I think the person was telling us. Oh, anyway, here, red wire goes from there. So that means red usually means positive, and this person is connecting this red on this one here, positive terminal of the battery. So that means current goes like this. So we are interested here. This portion is on the magnetic field, right? So current is going this way, left. That's what I see, at least, right? So left, it's going left. And see, the magnetic field is going from north to south, right? North to south. So magnetic field is up and current is to the left. So dodge your thumb points inward. So you have to crawl your fingers upward in this case, right? You have to crawl your finger upward. So make sure to orient your, so that's where this breakdance thing comes in. So you need to orient, nicely. Okay, so, and now you can do reverse the fingers, just to reverse the direction of finger. Direction of magnetic field is still in the same direction. So you are curling your fingers up, okay? And now thumb goes opposite, okay? So yes, so that's how current carrying wire experience force. And it's actually moving charges that are experiencing force. And those charges on the wire, so that means wires also experience force, okay? So now, let's write this equation in terms of current. And basically, when we were writing the equation, the new unit for the V, we already did that. So let's do that one more time here. So in this case, we want to write in terms of current. And current is charge over time. Where is time? Hey, time is in velocity. Remember, velocity is displacement over time. So I can use that. I want current, and current is charge over time. So where do I get time from? Velocity. So let's split or use the definition of velocity. So that gives me this. So now this charge divided by time is the current. See that? So now that's that. What is delta x? Delta x is the path or distance through which the charge moves during that time interval delta t. So that means what we can do is we can replace that delta x by length of the wire, okay, in the magnetic field, length of the wire on the magnetic field. So that's that. Hey, that's the equation for the force on the current. It looks very similar to the force on the charge, and rightly so. It's the same idea, okay? So now, current, although we say current is flowing left, right, and so on, in terms of physics, it is not a vector quantity, but displacement is. So that's why you see the arrow is stuck on this length, okay? But which side is this displacement? Displacement is in the direction of flow of charge. So that's why we're gonna just use the direction of current flow as the direction of the length, okay? So to find the direction of force, that's why we line up our fingers in the direction of flow of current, okay? Okay, so that's the force. So if we want to write in terms of angle, we can do that. Okay, so just sine theta, just like we had for the field. Okay, so now we can solve problem like this here. So yes, I see hand. Yes, Levi.
Wait, so what is length, or what is L?
Length of the wire on the magnetic field. So that
Okay.
means we are assuming that the charge, or we can say whatever the length charge travels in a unit time.
Why is that a vector, not a scalar?
Remember, the delta x is a vector. So length is just, we are saying that's the length. Delta x we are saying as a length.
Oh, okay, I see.
Okay. Yes. Good point. How come length be a vector? Length is a scalar, right? But we are just saying that's the length of the wire where the displacement of the charge is taking place. So we have to go to the source. So when we do that, it's visible. So that's why sometimes I like, when, especially when these derivations are simple, I like to show those derivation, okay? That gives us intuition how things are working here. And I'm theoretical physicist. All physics I do is through the mathematics, okay? So I like that. So how do we solve this problem then? I really appreciate your help, and I think it's gonna help you to think about it, right? And when before you start solving problem, if you think a little bit hard, do the brainstorming, that thing sticks in your head a bit longer than just just watching somebody else doing things. Okay, so that's why I really encourage you folks to think hard before actually start copying this. So, and when you give suggestion idea, it helps me too. How the current comes here in. Okay, so excellent point. So I see one question on the chat, how the current comes in there. So yes, we have to connect battery somewhere. Just like we saw in the last demo, right? There was a battery and wires. So that's how we need to connect. Okay, so for convenience, we may not show all the part, right? But yes, we need to connect like that. Yeah, that's a good point. How come there be a current without batteries or anything like that, right? We don't see current battery connected here, but we can always connect battery and so on, which is not shown here. Okay, good point. Thank you for bringing that up. And there is a very excellent question. Should we assume that theta is 90? So the wire, yes, we can make it, like different angles, and the angle information is not given. So what we can assume is, yes, we can assume it's a 90 degree. Yeah, that's a good point. Is that left for you folks as well? Yes, great. So again, the question might be, where is current coming from? So when we need to supply current, of course, we want to open this thing up a little bit here, open this thing and connect battery, which I'm not showing, okay? So this, let's suppose it's going something like this. So this wire we can orient, okay? We can orient. So length in one side, let's say L1, width, let's say L2. So L1 is given, and I made L1 longer side, so maybe I should write 30 centimeter for L1, right? And L2, let's say 20 centimeters. And the current that's flowing, I, in the loop, hey, 1 ampere. I like that simple number. And magnetic field is 2.5 Tesla. So now the question is, what is force? So assuming theta 90 degree, or we can just write theta for the, for the moment, but I think it's going to be easier, just plug in theta 90. So what happens? F gonna be I times L times B, and sine 90. So this is basically 1. And if it is not 90, less than 90, what happens? The force is still going to be there, but value going to be smaller. Okay. So now we can find the force. Now let's say force on L1, right? So let's say F1 is force on L1 gonna be I L1B, and force on L2 gonna be F2 I L2 B. See, it's the same magnetic field, right? So that's that. So now, what happens? When this is 90 degree, when one of these is 90 degree, let's say when B is 90 degree to L1, the B is how many degrees? Huh, that's kind of interesting. Oh, let's go this way. Okay, looks like I'm doing, so this is just, okay, right? Magnetic field is going something like this. You see that? And our longer part is this way, right? And let's say magnetic field is going that way. So when magnetic field is perpendicular to this side, what happens magnetic field to this side, L2? 0 or 180 degree. Do you see that? Right? And we know this is 0. So this part does not experience force. Only these two parts experience force. And you see that those currents are moving in opposite direction. So why 180 degree? That's a good point here. So this upper side, let's say this is, this current is flowing in the same direction. Remember, to find the angle, we need to look at the direction of flow of current and the magnetic field. Let's say if they are pointing in the same direction, that is 0. But down here, since this is current is going in the loop, down here it's going to be opposite, just like we see here in our sketch. Over here it's going right, and this is going left. So that's why one is 0, another one is 180 degree. Good point, Jessica. So now, so you can just plug in those numbers and find the value of force. How about direction? So what I can say is, yes, you can figure out direction, and direction in one side versus direction in another side, they're going to be opposite. Okay, direction, if direction on this side is like this, okay, coming towards the screen, and direction on the other side going to be opposite. Okay, direction going to be opposite because direction of current is opposite, means direction of force going to be opposite. So then what's going to happen to this coil? You are applying force in this direction and that direction in this coil. Hey, it's going to spin. It's going to spin. It's going to spin. Yes, Laura, you got it. Okay, it's going to spin. And that simple thing allows us to make electric motors, electric generators, and so on. So you put magnetic field, I should say electric motor in this case because we are supplying current. So all the electric motors, all the electric device that spins in your home, blender, right? And of course, you can name other devices. I may not have that many devices, okay? and there can be fan that's spinning. All of them have electric motor. So what happens? There is coil inside the motor, and you pass current. Current now flows, and there is also magnets. Okay, so the coil is sitting between magnets. So next time when your something breaks, and before you throw, go ahead, break it more, open it, and see if you can find that coil. Okay, and you may also find magnet. You will find magnets. Hey, you get magnet out of that, and magnets are fun to play with. I have one. See, I have another one, and what happens? Yeah, see, fun to play with, isn't it? So now you know where to find magnet. See, this problem is not just a problem. There is a lot of things in this problem, and it gives you whole principle, working principle of motors, generators, and so on. Okay, so that's the same question. Okay, so now let's do a little bit twisting of our hand. Okay, a minute.
So does current have a different right hand rule from just a charge?
It's the same. Remember, current flow is just the motion of positive charge in that direction. That's what that is, right?
Okay.
Oh, okay, 30 more seconds. So dot is out, cross is in. Dot means out, cross means in. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see if I still remember how to use right hand rule and figure out what the correct answer is. Oh, I need to use my right hand, means left hand. And which way current is going? Am I pointing my fingers in the direction of current flow? No. Okay, so I have to go this way then, right? Now, see, I can do this up, palm up, because the hill is up, so that I can easily crawl. If I were to start like this, I cannot crawl it up, right? I cannot crawl it up. So yes, so that's that. So that's good. So my thumb should be the direction of the force. My thumb should be the direction of force, right? So it looks like my thumb is not going towards the screen, not towards the screen, but out. You see that? Do you see I have that thumb over there? Of course. So yeah, looks like oh, where is my, oh, right here. Yeah, mostly D, and there was few C. I guess inverse is out. We got confused a little bit. Okay. So this is what I'm talking about. So wherever you see electric motor, this is what electric motor has. Magnet, permanent magnets. Actually, you can find, yeah, they may be, usually they put that in kind of circular form, okay? So they may be look like this, and coil may not be exactly rectangular, maybe circular, and of course there are 5 or 6 coils going around to make it more efficient. But this is the basic principle, okay? So force are going in opposite direction, just like we talked about, right? So current going up, down like this, right? So this is goes to the outlet where you plug your thingy, right? So now magnetic field is going like this, okay? So that's the force. And what happens? Force gives you, force times lever arm gives you torque. So when something is rotating, that means it's a torque that's acting, making it rotate, right? So all the forces are acting equal and opposite. So that means the coil is not moving from one place to another place. Net force is 0, but net torque is not, okay? So that's what that is. So now I can use this force, and lever arm means, in this case, let's say simplest situation, that's going to be half the width for each of those. So this being axis of rotation here at the center, this is going to be half of the width, okay? So we can use that and write something like this. So this is torque in one side, because we are using force in one side, so that's the torque in one side of the coil, but there is torque in the other side as well. So we can double it, okay? Both torque gonna act, let's say in this case, looks like they're gonna make it spin, clockwise. So both of them are acting in same. So we can just double that. So that way this 2 and 2 cancels, giving us very nice one there. And this L is length of the coil and W is width of the coil. Now what we can do is we can multiply length and width and make it area. Now with that, what happens? Hey, even if it is not rectangular, rather it's a circular, like this, it's gonna work, okay? It's gonna still, we can make it spin, still make it spin. Now A gonna be area of this coil. And usually they have this, circular kind of structure. So that gives you a torque, and that's the torque that makes it spin, okay? So now we say, okay, that's the angle between A and B. Now, what is A? What is the direction of A? Now, that's a tricky. That's tricky. So, its direction could be going this way or this way. I almost poked my nose. Okay, could be going this way or this way. Okay, the area we take gonna be always perpendicular. Now, is this way or that way? How do we determine? So for that, we need to look at which way current is flowing, okay? Which way current is flowing. So once you know direction of current flow, and here comes the another use of right hand, grab that coil with the fingers. Grab that coil with the finger, thumb points in the direction of area. I'm just holding coil with my hand, so ignore this. So just think about this. Grab this with the fingers in the direction of flow of current. And we're going to be using this technique a lot. We may call this second right-hand rule number 2, okay? So if current is flowing all the way around, then what I have to do is I need to turn around and this thumb points downward now. Upward, downward. You see how the current is going this way versus current is now coming towards me, going towards the screen. That's how we use it, and that's the value of the torque. So larger the torque, larger gonna be the angular acceleration, right? So that's how you spin it, and that's gonna give you, and that spin gonna induce EMF. Or let's say, oh, for the motors, we just want that thing to spin, isn't it? That's all. Okay, so it looks like it's already break time. So let's do that. So I see this question here. So I'll come back to the question on the chat after the break. So basically, N is also given. Looks like I did not list it. So we have everything now. Okay. So these 4 things, and that's what we have in the formula. So it's just plug and chug after this. Okay, so I'll let you work on that. And the unit of torque, remember torque is lever arm. Lever arm times force. So unit of force is Newton. Lever arm means just it's a length. Okay, so that means it's a meter. So that means its unit gonna be Newton times meter. So now when theta is just so part B, it says theta is just 10.9 degree, everything else is same. So that means it's not going to be max now. It's going to be less than whatever you calculate here. So for this, you need to use this whole thing here, NIAB sine theta. And theta is that. So this number going to be way smaller. And unit is still same. Okay. And these days we use digital meters like this, but you know, we may also have this kind of meter that has a pointer that indicates the value, analog we say. Okay, So in that case, this meter worked at the same principle. More current flows, more deflection there are gonna be, means larger number, okay? The same principle that meter uses. So Levi, is that new hand or the old hand?
I had a question on the other problem.
Okay.
I'm confused what N is supposed to be.
Oh, the coil, let's see. In this formula, what happens? This is, we are just talking about being just one coil, okay?
Okay.
One turn in the coil. So now, this is N is equal to 1. Now, if I make this is now N is equal to 2. 1, 2. And there are several of them in real application.
Okay, thanks.
See, you see that here, that's a spinning here. There are so many turns. Now, when current is flowing through the wire, what happens? It produces a magnetic field. When current is on the magnetic field, it experiences force, we said, right? When current is in a magnetic field, so there is magnet, there is current, right? There is magnet, there is current, let's say. It experiences force, and we learn how to calculate force experienced by the current flowing through the wire. We learned that. ILB sine theta. Okay, so that was the formula. Now, what happens is the experiment shows that if we pass current through a wire, just like you see here, there is this wire, and we are passing current through this wire. And there are these tiny magnet, the not magnet, but the iron dust. Okay, these are the iron dust. And you see this iron dust, they circulate. In this picture, what do you see? The wire, and current is flowing through that. And this is compass. You see that? So compass compass lines up with the magnetic field. And here, when we turn off the current in this wire, what happens? These compass, all compass lines up in the same direction, which is not shown, right? But when you turn on current, what happens? You see that? They are kind of forming circle. You see that? They are lining up such a way that they are forming circle. So what it means? That means current flowing through the wire produces magnetic field that goes in circle like this. Okay, that goes in circle like this. That's what it is saying. And now suddenly makes sense why this one experienced force. See, this is magnet, let's say, and current in the wire is also magnet. See, it produces magnetic field, means it's also acting like a magnet. And we know two magnets, there is force between two magnets. So it makes sense. So now, the right-hand rule I was talking about, again, now this is, this is another right-hand rule. We call that right-hand rule number 2. We may say it, okay? But basically, it's the same thing. You crawl fingers in a particular direction to find the information about something else. So in this case, what's the direction of magnetic field that's circulating because of the current that's flowing up? So what do? You grab that wire, something like this, with the fingers curling in the direction of magnetic, hold on, with this thumb pointing in the direction of current flow. Thumb in the direction of current flow, okay? And then once you crawl fingers, the fingers gives you direction of magnetic field. So when current is going something like this, see my fingers is curling like this. Now when current comes down, so that means I need to bring my thumb down, means my finger now curling exactly opposite. Okay, and so that's how we use it. And what's the value of magnetic field at a distance r from the wire? That is given by this equation. Okay, and this is new constant now. So we had electric constant K, and we learned that K is 1 over 4 pi epsilon naught. The epsilon naught was another form of electric constant. Now this is a magnetic constant, just like electric constant, okay? We call that magnetic permeability, okay? Magnetic permeability. So the value is at distance r. So the value of magnetic field changes with distance. If you are close to the magnetic field, close to the current carrying wire, you have stronger magnetic field. As you go farther, you have weaker magnetic field. But what's the difference between electric field and magnetic field? So electric field is produced by charge, right? And it is 1 over r square. But magnetic field is produced by current carrying wire, and it is just 1 over r. Okay, so that means the magnetic field can extend to a longer distance. Okay, it can extend to a longer distance than the current. It can remain stronger up to a longer distance. But electric field being 1 over r square, it dies down a bit quicker. Okay, its value is this. It's a small number. Okay, and from here we can figure out the unit. It's going to be Tesla meter over ampere, where Tesla is the unit of magnetic field. Okay, m is the meter, means that's the unit of r, distance at which we are measuring the magnetic field. Okay, and I is the current in ampere. So now let's do a little practice of finding the magnetic field. And remember, magnetic field, if magnetic field is in same direction, they add up, right? If they are in opposite direction, cancel. Keep that in mind. To answer this question, by the way, did you do practice of using this second form of right hand rule? I have this wire, I can grab this wire. If I know current is flowing this direction, I can grab something like this. Okay, by starting, by pointing thumb in that direction, and crawl gives you the direction of magnetic field. Okay, and remember here, so think about, so now maybe I'll use just pencil, it's going to be easier. So pencil here. So now, depending on what point I am looking at, direction of magnetic field going to be different. So here, when I'm looking at this point here, it's pointing that way. When I look at here, it's pointing slightly different, opposite, right? Here versus here, opposite. You see that? So you need to point out what point I want direction of magnetic field. Okay, so for example, if I'm looking at this point, and if current is going up, let's say, then direction of magnetic field gonna be this way. The circle gives you field lines. Okay, the circles are the magnetic field lines, and magnetic field gonna be tangent at that point. magnetic field going to be tangent. Let's keep that in mind. So here it's going to be pointing this way, and other side is going to be pointing this way. Okay. So we need to look at magnetic field at a point. So that's why this question is asking you, look at the magnetic field at point 1, at point 2, okay, point 3. So near point 2, there are two currents flowing, right? Here also there are two currents flowing at 3, okay? So that's that. So now I'll let you work on this. So before I turn this on, so Levi, is that hand old hand or the new hand?
Sorry, that's old.
Okay, I just wanted to make sure. So 2 minutes. Looks like it may take a little time. Oh. So take your time. Oh, 20 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, how do we do it? So it looks like the current is going that way. So that means magnetic field is coming something like this. So getting out, magnetic field is getting out at that point, at point 1. I'm looking at point 1 first. Okay, point 1. So what's happening here? Magnetic field is coming out in this side, going in this side. So at that point, it's coming out. Do you see the same thing? Now at point 2, this one, what's happening? Magnetic field is coming out on that side, right? And when it goes like this, it's going to be going in. So this is due to this current, and this is due to this current. Looks like they're going to cancel each other. Because they are in opposite direction. Now, how does the 3 looks like? Looks like current is flowing in same direction near point 3. Did I get that right? So near point 3, what's happening? It's like that. So that means both of them coming out. So it looks like this is gonna be the strongest. 3 gonna be strongest. And since there is no cancellation here, then gonna come 1. And weakest gonna be 0.2. 3, 1, 2. 3, 1, 2. Oops. None of them are 3, 1, 2. Hey, you folks mostly figure out already. Okay. So now, one wire is like a magnet, another wire, let's say if there is current in another wire, that's also magnet. So depending on what point we are looking at, what's going to happen? Let's see, there are going to be force between 2 wires, just like there is force between 2 magnets. So now let's suppose we have this wire, and on this side, what happens? Magnetic field is going in. Do you see that? Can you confirm that by actually grabbing that wire or your pen or pencil, right? Grab it and see, indeed your fingers are curling into like this, not out. So in this side is going to be out, but this side is going to be in. Okay? From this side it's coming out. You can see these fingers coming out from this side. And on this side, they are going in. See that? Those fingers going in on this side, coming out on this side. So that's how I look at. So that's one wire. Now, let me put another wire. Oh, that's the magnetic field. We learned that, right? So if, at distance r, the magnetic field due to current carrying wire I1 is this. That's Ampere's law, we said. Okay. So now let me put another wire in that magnetic field that is carrying current. Okay. So now what happens? Now for a moment, forget about this one here, this current here. Forget about it. Just think about this wire is sitting on a magnetic field, right? Just I2 is sitting on this magnetic field. Forget about where the magnetic field is coming from. It's just sitting it there, right? So now can you figure out what's the direction of the force gonna be on that wire that has current I2? So now you are figuring out force, right hand rule number 1. Okay, start by fingers in the direction of current. Fingers in the direction of current and crawl fingers in the direction of magnetic field. In the direction of magnetic field. And force is left, to the left. Yes. Force is to the left. Okay, so what's the value of that force? We already know force on current carrying wire is I times L times B times sine theta. Here angle is 90 degrees, so we can just write like that. And the magnetic field here is coming from current I1, so that's that. Hey, that's the force between two current carrying wires, just like force between two masses, force between two charges. Now we have force between two wires that has current in them. And that force depends on both currents, I1 and I2. Okay. And now, if it is force on I2, then it depends on length of that wire. Okay. It depends on length of that wire. Whatever. So if I am looking at force on this, then you need to put length of this. If I am looking at force on this, then you need to put length of this one. Okay. So it looks like now we have new hand. Levi?
Sorry, I still had a question on the last iClicker. I saw the same problem on sapling for the bridge assignment, and they had a different answer.
Question, is that the previous slide or we are talking about this one here?
The previous iClicker question. Oh, I'm so sorry. I just don't understand.
This one here?
Yeah, I got 312 because I thought for 3 they would add up.
Biggest to smallest, right? Do you have that question handy? Can you share that?
Yeah. Oh, okay.
Looks like dot was between the wire.
Yeah, I think that's what threw me off. Sorry.
Yeah, we need to pay attention to that dot. Yeah, that may confuse you. Okay, yes. So now we can look at what's the force on current I1. Okay, what's the force on current I1? So field is now coming from the wire I2, so you can use that, and you can see your fingers going to be coming out on this side, right? So if you look at this hand again and imagine green wire being this, you are looking at this side of the green wire, means field is coming out, so that's why dot. Okay, now this is sitting on field that's coming out. So now which way the force going to be? Right. And what's the value? The magnetic field times length and times the current. Okay, so again, it depends on both. So now what's the difference between force on one versus force on another one? Just difference in length. Here we have L1, here we have L2, right? Only that's the difference. So now the force is acting like this, means they are attractive, right? So attractive force. So these wires, if current is flowing in the same direction, they have tendency of pulling closer to each other, okay? And now let's say if you were to reverse one of these wire, what's going to happen? So that's for you, and this is also for you, okay? So now we are looking at this point here. There is this charge. So charge is moving here, and why does it experience force? Because there is a magnetic field due to current, this current and this current. And we are looking at point between the wire, in between the wire. So first look at how the magnetic field acting. Are they going in or coming out? Are they canceling or not? And so on. So if magnetic field is 0, force is going to be 0 for sure. Okay. So if magnetic field is not 0, then they're going to be force. And once you figure out what direction the magnetic field is, net magnetic field, then you can figure out the force. Okay, force. So this charge experiencing force if there is a magnetic field. Okay, and what's the possible source of magnetic field? This one and that one, currents. Okay, so I'll let you work on this, and maybe minute and 30 seconds should do it. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. Hey, it looks like answer is again E. Why is E the answer? So first, let's start by looking at the field due to each wire. So this is going like that. Looks like going in at that point, right? And over here, hey, coming out. Opposite. Cancels. Now, what current is same, right? Current is same, and this Q is in the middle, so R is also same. So that means value of magnetic field is same, but direction is opposite. So they actually becomes 0, B. So once B is 0, F is also 0. Yes, so that's why looks like E is that E? No magnetic force. Yes. No means 0. Yes. Looks like it's almost 50, so may not have enough time. So we'll start from here next time. It's going to be also like a review for what we did today. And then going to move, and we need to move to another chapter, don't we? Yeah, these coils give you magnetic fields and so on. So yeah, almost done. So we'll come back here and then move to another chapter next week, okay? Okay, folks, have a good weekend. I'll see you next week.
Thank you.
Thank you.
Thank you.
Thank you.